Hello everybody, I'm Chris Williams and welcome to part 3 of Astrophysics Chris, where I, Chris Williams, revise for my exams which have been held in October 2010, and I effectively embarrass myself on YouTube by sharing with you what I understand about what I need to know for the exams. Essentially me reading out to the camera what my notes are, and me getting myself confused as I progress. And of course, I understand that here in the United Kingdom, the economy dictates that you yourself might not be going to university anytime soon because there aren't enough places available. So I hope that if you are watching this, you are agreed to share my passion for astrophysics. So I hope that I will educate you with university level material, and if you like, we can engage in some astrophysical discussions. Right, so we're nearly 1 moment in. I've got to be careful that I don't overdo the time limit because of the 10 limit YouTube time limit. Right, so measuring star formation rates is the topic for this third video. In my previous 2 videos, I have revised that faraway galaxies seem brighter than closer galaxies. The greater the redshift, the brighter the galaxy, because of something called the K correction. It's all to do with dust that is present, and the dust makes the object that's far away seem brighter. And here today we're talking about short-lived but luminous O and B stars, and they ionize the dust that surround them, and that causes strong Balmer emission lines. And from these strong Balmer emission lines, it's a kind of indicator as to the level of star formation that is present. Because when dust is absorbing the emitted radiation, causing a kind of scintillation effect, that's called extinction. Longer wavelengths are less prone to dust extinction, so hydrogen alpha has an advantage when you're looking for spectroscopic lines to determine how many stars there are present. Infrared spectra, I mentioned infrared in my second video, that can be measured, but not in such large numbers as optical spectra because of technological limitations. Shorter wavelengths, on the other hand, are dominated by lower dust absorption, so longer rest frame wavelengths. Objects far away are in the rest frame, us here on Earth in the moving, observed frame of reference. Rest frame wavelengths directly sample more of the star formation, but hydrogen alpha is still a long way from being an extinction-independent measure of star formation. So essentially, these notes saying that hydrogen alpha and Balmer emission lines are what you're looking for when you want to measure the rates of star formation. The energy absorbed by the dust in star-forming regions does not go away. Obviously, lots of energy taken out of the system, so to speak, when the energy is absorbed by the dust. Right? Of course, that leads to thermal emission. Right? It is radiated as thermal radiation, indeed, as I just said, and the peak emission from the dust is roughly around 70 to 150 micrometers. In the Milky Way galaxy, the ambient interstellar light hits the ambient dust, and the thermal radiation from that dust has been detected by surveys such as IRAS and the Japanese Akari telescopes. Now, this dust has come to be known as cirrus, but it looks like the cirrus clouds that you see in the sky. And radiative transfer models predict that these so-called cirrus clouds, their contribution is cooler than the clouds in which star formation is going on. Supermassive black hole accretion in the galaxy's active nucleus also eats dust, as I'm sure you know, and that is in a torus. And models predict this contribution dominates in the mid-infrared rather than at longer wavelengths. Far infrared measurements capture the star formation, but are not free of the interstellar mass function assumptions, because massive stars dominate the heating of the dust. That's obvious. The hotter the radiation, the more the dust will absorb. Star formation rate indicators rely heavily on different physical processes, according to the notes, and is independent of dust obscuration. And indeed, this factor is known as radioluminosity. We're 5 minutes into the video now. Supernovae from massive stars accelerate charged particles, as you know, if you know a lot about neutron stars. Now, this brings us on to synchrotron radiation. You can detect synchrotron radiation from the Earth. Now, there's X-ray radiation and other sources of radiation given off, indicating that although the source be practically invisible to the naked eye, you will detect it through detectors. And of course, magnetic field obviously present. This illuminates what we know about quasars and other black hole physics related issues, and certainly true as star formation is concerned, because we've got the dust that's present being collimated into a torus, indicating that there is some kind of heating effect going on. Right. The angular resolution of far infrared images makes it difficult to identify which optical galaxy is the main far infrared emitter, but stacking analysis such as averaging is used. So that's where you've got loads of galaxies and you average out you average out the data. So you can see what the relationship is between each of the galaxies that you're observing in the far infrared. You're looking to see they correlate with bolometric luminosities. Right, so why should mid-infrared correlate with far infrared luminosities? Well, the dust emitting the mid-infrared light is physically distant from the far infrared emission. In order to be radiating at short wavelengths, the dust must be hotter. It turns out that the dust grains are small and transiently heated sometimes by a single photon. So faraway objects heat the dust with at least a single photon. I know in earlier notes that there were some instances where 2 photons are heating the gas. And indeed, if I click on my notes, for every 2 photons created by stars or black holes, 1 photon is absorbed by the dust, and that energy is re-rated as thermal emission by the dust. So you've got 2 photons being for every 2 photons emitted, only 1 photon has an effect on the dust. One disadvantage of using mid-infrared for estimating star formation rates is that black hole accretion can also contribute. The dust tori in active galactic nuclei are predicted to emit at the peak of their radiation at exactly these wavelengths. However, the thermal spectra from dust tori are largely featureless, so mid-infrared spectra can in principle distinguish star formation from black hole accretion. So, essentially here we're trying to determine how you can tell the difference between when star formation is occurring and when dust is being heated by black hole accretion. You've got tori around where there is a black hole, and also in the clouds where star formation is occurring. As I emphasised at the start, you can tell spectroscopically by looking for strong Balmer emission lines and also hydrogen alpha lines. You can use them as tracers as to whether there is star formation going on, but this can be unreliable, I get the impression the notes are saying. Right, I hope you'll join me for episode 4 of my revision notes, where I will be talking about multi-wavelength surveys and, at this time, the history of cosmic star formation. Right, I hope that you will join me next time, and I hope you get into university yourself so you can learn this material yourself. I hope I've whetted your appetite for your astrophysics. And also, my exams in October. I'm currently recording this on August the 16th, 2010, so I hope that this is going to develop my confidence and also boost my knowledge of this subject ahead of these exams. Okay, thank you for your time, and bye for now. Bye bye.